Okay, half reactions. Request came in to do a couple of examples, so let's do that. First, let's review. We got oxidation, reduction. Half reactions, of course, show how electrons are being exchanged in an oxidation or reduction reaction. Some ground rules here. We got losing electrons, oxidation, gaining electrons, reduction. If we're going to write an oxidation half reaction, the electrons go on the right because they're being released, they're being given off. If we write a reduction half reaction, they're going to be written on the left because, of course, they're being gained or GER. So let's start with a simple one. Let's take the reaction of H2 plus O2 makes H2O. Remember, first step is to assign your oxidation states. If we have elements that are by themselves, their oxidation numbers are 0, plus 1, minus 2 for, you can see that, for hydrogen and oxygen. Okay, so hydrogen, H2. This is the oxidation half reaction because you can see the oxidation number goes from 0 to plus 1, which means it's being given off. H2, we're just going to write it here. Let me write the oxidation half, or the oxidation state like that. And then we write H2 plus 1. Now, the question is, so to determine the electrons, determine the number of electrons, it is quantity making sure that's coming through, yeah. Quantity of the element times change in oxidation state. So, quantity of element. How many hydrogens are there? There's 2, not 4, because remember, it's the same stuff. It's there's still only 2 because this is before the reaction, this is after the reaction. So it's the quantity, 2, times the change in oxidation state, which is 1. 2 times 1 is 2 electrons. So how many electrons does it take to change 2 hydrogens from 0 to plus 1? It takes 2. Next, we have our our reduction half reaction, O2. We're just going to write the oxidation number here. Draw our arrow. Oh, I didn't balance this thing. Ay, 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 ay. All bets are off. You know, what an embarrassing amateur mistake. You know, this is the part where, had I not been doing this in front of a camera, somebody in the back would have been like, don't you have to balance that? You over there, kid? Yep, you are correct. Okay, so let's balance it. Put a 2 here, and then we got to have a 2 here. Okay, so sorry about that. 2H2. Forget this orange pen, marker. 2H2, this oxidation number is going up, so it's oxidized. I can write my arrow, 2H2 plus 1. Okay, back to reality. 4 hydrogens here. Each one goes from 0 to 1. So if there's 4 hydrogens, each with a plus 1 change, that of course means 4 electrons. Now, oxygen, O2, if an easy way to do this is to know that if 4 are being given off by 1, 4 must be being gained by another one. That is to say, you must conserve charge. And then we write 2O minus 2. So, where do I get all these numbers from? Let's try purple. This we write just copied straight away. The 2 and the O, we just write copied straight away with the oxidation number there. And then we figure out our 4 electrons. You can see this here, 2H2, goes just like that. 2H2 goes just like that, and then the charge follows. Make sure the charge is balanced. Good to go. All right, let's try a couple of tougher ones now. Working from the problem set, this is number 3. On the problem set, we'll start off with part A. Got this written down here. Organize this out a little bit. So we got 3SN plus 4HNO3 plus water. Hopefully I have enough room. 3H2NO3 plus 4NO. Can you see that okay? Yeah, it looks like you can. Okay, let's start by assigning these oxidation numbers. Now, of course, assigning oxidation numbers takes a lot of practice, but for any of these compounds, it's very easy to quickly Google what the oxidation numbers are, and you can check your work. So, if something is by itself, as is in the case of tin here, it's 0. I'm going to just whip through these very quickly in the interest of time. Plus 1, plus 5, minus 2, plus 1, minus 2, plus 1, plus 5 again, minus 2, and then plus 2, minus 2. Okay, now, we don't have to, there's a lot going on here. All you have to worry about is to figure out what oxidation numbers change. You don't have to worry about every single oxidation number up here, just the ones that change. So we can see that tin has an oxidation number that, where did I forget to write something? Right here. H2SNO3. It's just embarrassing, you know? Absolutely embarrassing. Okay. Did that change my answer here? So plus 1, minus 2. So yes, this would be plus 4. Is that right? Minus 6 plus 2. Yeah, plus 4. Okay. Yeah, that's what I have in my answer key anyway. Okay. So tin. 3SN0. Again, just writing it straight away. We can see that the tin oxidation number went up, so we're going to write the electrons on the right. Again, if it's losing electrons, the oxidation number is going up. See the previous video for more details on that. I'm going to write 3SN plus 4 because I got my act together and wrote it the right way now. So you can see it's quantity times change in oxidation state. The oxidation state went from 0 to plus 4. So that's a change of 4 times 3 of them. Well, if it takes 4 electrons to go from 0 to plus 4, and there's 3 of them, 4 times 3 is, you got it, 12. 12 electrons. Now, what's the other oxidation number that changed? If one oxidation number went up, the other one must have gone down. Scanning around here, it looks like it's a nitrogen. So we got the 4 here. Excuse me, we got the nitrogen here and here. Okay, well, there's 4 nitrogens at plus 5. Again, if this lost 12, this must be gaining 12. And this is going to go to 4N plus 2. Let's see if the math makes sense. We've got nitrogen changing its oxidation state from 5 to 2. That's a change of 3. And there's 4 of them. 4 times 3 is 12. It makes sense. Tin is giving off 12 electrons. It's giving it to the nitrogen. Everything balances out. Let's try another one. That was part A. Next we will do part B. Pharrell's been looking at me weird this entire thing. I'm not sure how I feel about it. Keeping an eye on you, buddy. All right, next one we have an iron hydroxide, 2FeO2, FeOH2. That's going to get dropped in peroxide, and it's going to react to form 2FeOH3. Okay, let's assign oxidation numbers. Fe is plus 2, minus 2, plus 1, minus 2. Again, this is the peroxide ion. If you look at your reference table right here, the oxidation number is -2, but remember it says selected oxidation states, which means that's not every oxidation state that's possible. This is the peroxide ion. If you look at your table of polyatomic ions, it's an exception. Why did I write -2? Why did I write -2? Don't know. Should be -1. Okay, sorry. So this is +3, this is -2, and this is +1. Okay. Now, what oxidation number went up? Remember, if the oxidation number goes up, it's because it is losing electrons and it is oxidized. So with that in mind, you can see iron went from +2 to +3. So all I got to do is write 2Fe +2. Reacts to form. It's being oxidized, so I write the electrons on the right. 2Fe +3. Now, again, quantity of element times change in oxidation states. There are 2 irons there. Each one loses 1 electron for a total of 2 electrons. And now we got to find the thing that was reduced. Well, what do we got? Looks like the oxygen goes from -1 to -2. That's on the reactant side. So I write O2 -1 plus 2 electrons. Reacts to form 2O -2. We've balanced out the number of oxygens. Each oxygen went from -1 to -2. That's a change of 1 times the quantity. 2 means 2 electrons. There you go. So we got our half reaction for iron, half reaction for oxygen. Good to go. That was 3 on the problem set part B. Wrote it up there now that we're done. Good job, buddy. Now we're going to write part C because we're going to do part C. Da-da-da-da. So we got sodium, 2 moles of sodium, reacting with 2 moles. Is that 2 moles of sodium? Yeah, 2 waters. Reacts to form 2 sodium hydroxide. And probably hydrogen. Yep, H2. Okay, quickly assigning oxidation numbers. We've got 0, +1, -2, +1, -2, +1, and 0. Yeah, okay. We got sodium. You can see 2Na0. It's oxidized. Metals tend to be oxidized, so my eyes goes there first. 2Na +1. You can see the sodium goes from 0 to +1, and there's 2 of them. That makes 2 electrons. Again, number of electron is the quantity of the element. There's 2 sodiums there, times the change in oxidation state, which is 1. 2 times 1 is 2. Now we go to the element that is reduced, which is hydrogen. We can see that because the number is reduced, it goes down. 2H2 plus 1 is the charge initially. 2 electrons. And it goes to H20. So let's check. 4. Good. I'm glad we're doing this one. Okay. Let's do a gut check here. We have two hydrogens. Each one is +1. Now, you can see hydrogen splits up. Some of it makes the hydroxide ion here, OH. Some of it makes hydrogen gas. So, how many do we write down here? Well, you can see that for hydrogen, with it being in 2 different locations, in this location, hydrogen goes from +1 to +1. 2 of those hydrogens were not reduced. But you can see that 2 of these hydrogens were reduced. So it would not be appropriate for us to write all 4 down here because not all 4 hydrogens are reduced. Just 2 hydrogens were reduced. So what we'll do is we'll erase this 2 and focus only on the hydrogens that were actually reduced. So we write H2 +1, H2 0. Hydrogen goes from 1 to 0. There's 2 of them, and therefore it takes 2 electrons, and now the math works. Okay, so that's 3 redox half reactions. If you're going to move on to 3 Part, oh my gosh, part D, don't do it. We're going to skip that one. Skip 3 part D on the problem set. If you have any more questions on half reactions or whatever, please help me, or excuse me, please email me. Make another video to try and help you out.